There's an invisible ocean all around you right now. As you watch this, trillions of ghostly particles are streaming through your body without a trace. They're called neutrinos, and they're the universe's most elusive messengers, born in the hearts of exploding stars, in the fury of black holes, and even in the first trembling seconds after the Big Bang. These tiny phantoms hold secrets older than light itself. Yet, despite their abundance outnumbering atoms by billions to one, they slip through everything, through planets, through you, through the entire cosmos as if it weren't even there. But here's the wildest part. Some of these neutrinos aren't just passing through. They're relics, ancient echoes of the universe's birth, lingering in what scientists call the Cosmic Neutrino Background. And untangling its mysteries could rewrite everything we know about space, time, and how it all began. Picture this: nearly 14 billion years ago, when the universe was a seething, hot soup of energy, neutrinos were among the first particles to break free, racing outward as the cosmos expanded. Today, they're still here, a faint whisper from the dawn of existence, carrying clues about how galaxies formed, why matter exists at all, and what might lie beyond the edges of our understanding. But detecting them, that's like trying to catch smoke with your bare hands. These particles barely interact with anything, making them one of astrophysics' greatest challenges and most tantalizing puzzles. That's where this journey begins. Over the course of this video, we'll dive into 25 mind-bending mysteries of the cosmic neutrino background, from the way it bends our understanding of dark matter to the startling possibility that it might hide dimensions we've never seen. We'll explore how scientists are building colossal detectors deep underground, in Antarctic ice, and even in space itself to hunt these phantoms down. And along the way, we'll confront questions that sound like science fiction. Could neutrinos be the key to a theory of everything? Do they hold the blueprint of the universe's first moments? Strap in, because we're about to venture into one of cosmology's last great frontiers, where every discovery feels like uncovering a piece of the universe's hidden diary. And trust me, the entries will blow your mind. Imagine a river so vast it could fill the universe 1 billion times over, yet you can't see it, touch it, or even prove it's there without the most delicate instrument science has ever built. That's the cosmic neutrino background, an invisible flood of particles so ghostly they make light seem sluggish by comparison. These neutrinos aren't just passing through walls or planets, they're remnants of the universe's fiery infancy, left over from the first second after the Big Bang, when everything was 1 million times hotter than the sun's core. Back then, space was so dense that light couldn't even travel freely. But neutrinos, they slip through the chaos like whispers in a storm, carrying information from that primordial inferno straight to us. What makes them so maddening to study is how little they care about the rest of creation. Unlike photons, which bounce off your skin or get absorbed by your eyes, neutrinos could sail through a wall of lead stretching from Earth to the Moon and hardly notice. In fact, out of the trillions passing through your thumbnail every second, maybe, just maybe, one will interact with an atom in your entire lifetime. That's why spotting the cosmic neutrino background is like trying to hear a single raindrop in a hurricane. Yet this frustrating elusiveness is exactly what makes them cosmic time capsules. Because they stopped interacting with normal matter so early, they've been coasting undisturbed for nearly 14 billion years, preserving a snapshot of the universe when it was less than 2 seconds old. If we could read that snapshot, it might reveal why matter clumped together to form galaxies instead of scattering uniformly, or even why there's something instead of nothing at all. Some theories suggest these ancient neutrinos could be entangled with dark matter, subtly shaping the cosmos in ways we're only beginning to guess. To hunt them, scientists have turned entire mountains into detectors, like Italy's Gran Sasso laboratory, where ultra-pure tanks of liquid wait years just to catch a handful of neutrino interactions. Other experiments bury sensors in Antarctic ice or under the ocean, using the planet itself as a shield to filter out interference. Even with all that effort, we've only glimpsed the faintest shadows of the cosmic neutrino background. But those shadows hint at something extraordinary, that the universe's earliest moments might still be whispering to us if only we learn how to listen. The cosmic neutrino background isn't just a relic. It's a frozen scream from the universe's very first breath. While the cosmic microwave background shows us the cosmos 380,000 years after the Big Bang, the neutrino background takes us back further, to a time so early you could fit the entire history of human civilization into the next second. We're talking about a moment when the universe was a seething plasma, hotter than a supernova, crammed into a space smaller than our solar system. And locked inside these ghostly particles is a pristine record of that chaos, untouched for nearly 14 billion years. What's astonishing is the temperature. The neutrino background hovers at just 1.95 degrees above absolute zero, colder than deep space, but still carrying the faint thermal fingerprint of the Big Bang's aftermath. Compare that to the cosmic microwave background, which is a balmier 2.7 degrees. That difference might seem tiny, but it's cosmic detective gold. The microwave background is like a photograph of the universe as a toddler, while the neutrino background is an ultrasound from its first heartbeat. Why is this snapshot so hard to capture? For starters, neutrinos refused to play by the rules even back then. When the universe cooled enough for light to finally travel freely, photons got stuck in traffic, bouncing off matter for thousands of years before escaping. But neutrinos, they ditched the party a full second after the Big Bang, when the cosmos was still 1 trillion times denser than water. That early escape means they carry information from a time before the first atoms, before the first starlight, before everything we consider the universe even took shape. And here's where it gets weirder. Because neutrinos barely interact with matter, they've been streaming through the cosmos in near-perfect straight lines since that first second. No cosmic dust, no magnetic fields, no black holes bending their path. That makes them the closest thing we have to a flawless time capsule. The cosmic microwave background got smeared and reshaped by billions of years of structure formation, but the neutrino background, it's like opening a letter that's never been read, its ink unfaded by time. Scientists suspect these ancient neutrinos could answer why the universe looks the way it does. Tiny fluctuations in their density might have seeded the first galaxies, their gravity tugging matter into the cosmic web we see today. Some theories even suggest they're entangled with dark energy, subtly accelerating the universe's expansion. But to test these ideas, we'd need to detect a signal so weak it's drowned out by the neutrino equivalent of static background noise from supernova, the sun, even nuclear reactors on Earth. That's why researchers are dreaming up detectors the size of cities, using entire oceans or cubic kilometers of Antarctic ice as neutrino traps. The payoff: a window into the universe's most violent, creative moment, a time when the laws of physics as we know them were still being written. Here's something that sent shockwaves through the world of physics. Neutrinos, those ghostly particles we once thought were massless, actually weigh something. And that tiny bit of mass shouldn't exist, at least not according to the Standard Model, the rulebook of particle physics that's held strong for decades. When scientists first confirmed neutrinos had mass in the late 1990s, it wasn't just a small correction. It was like finding out gravity sometimes pushes instead of pulls. The discovery forced physicists to rewrite entire chapters of their understanding, and it's still shaking up theories about the cosmic neutrino background today. So how did we get it so wrong? For years, the Standard Model treated neutrinos as ethereal speedsters zipping through the cosmos at light speed, their mass so negligible we assumed it was zero. But experiments like Japan's Super Kamiokande and Canada's Sudbury Neutrino Observatory caught them in the act of something called oscillation, a bizarre quantum behavior where neutrinos switch between their three flavors, electron, muon, and tau, as they travel. Here's the kicker: oscillation is impossible if neutrinos are truly massless. It's like finding out a car can change colors while driving, except the manufacturer swore it only came in one shade. The implications for the cosmic neutrino background are staggering. If neutrinos have mass, even a minuscule amount, they've been subtly tugging at the fabric of the universe for billions of years. Think of them as cosmic sculptors. Their gravity might have nudged matter into forming the first galaxies, or even hidden vast reservoirs of dark energy we haven't accounted for. But the biggest head-scratcher is this: why are neutrinos so lightweight? The heaviest neutrino is at least 10 million times lighter than an electron, the next lightest particle. It's as if every other particle in the universe got a standard issue weight, and neutrinos somehow slip through the cracks. Some theories suggest neutrinos might be Majorana particles, a rare breed that are their own antiparticles. If true, it could mean their feather-light mass comes from a process so exotic it's never been observed. Others speculate they're tapping into hidden dimensions or interacting with undiscovered fields that only affect them. Whatever the answer, the neutrino mass puzzle isn't just a footnote. It's a glaring sign that the standard model is incomplete, and the cosmic neutrino background might be hiding the clues we need to crack it. To pin down their mass, scientists are staging audacious experiments. Germany's Katrin experiment, for example, uses a spectrometer the size of a building to measure the energy of decaying tritium atoms, hoping to catch neutrinos, stealing a fraction of it. Others are scouring the cosmic neutrino background for subtle distortions caused by their gravitational pull. But here's the wild part: even if we nail down the exact number, we'll still be left with the deeper mystery of why. And that answer might rewrite not just particle physics, but our understanding of how the universe assigns mass, and maybe even why anything has weight at all. Back in the 1960s, physicists faced a cosmic whodunit. The sun was producing neutrinos, lots of them, but Earth's detectors were only catching about a third of what they expected. This was the solar neutrino problem, a discrepancy so baffling it took decades to solve. The math was clear: nuclear reactions in the sun's core had to churn out electron neutrinos at a predictable rate. Yet experiments like Ray Davis's Homestake mine detector, buried under a mile of rock to shield it from interference, kept coming up short. It was as if the sun's factory had a leak, and no one could figure out where the particles were going. The breakthrough came when scientists realized neutrinos weren't disappearing, they were changing. Like chameleons mid-flight, electron neutrinos from the sun were morphing into muon and tau neutrinos on their way to Earth, slipping past detectors tuned to only one flavor. This phenomenon, neutrino oscillation, was the smoking gun proving neutrinos had mass, and it turned particle physics on its head. But here's where things get eerie for the cosmic neutrino background. If neutrinos can shapeshift, could some have transformed into versions we still can't detect? There's a haunting possibility that the CNUB isn't just made up of the three neutrino flavors we know. Some theories suggest sterile neutrinos, ghosts even to other neutrinos, might exist, interacting only through gravity. These phantom particles could be hiding in plain sight within the cosmic neutrino background, subtly warping the universe's structure without leaving a trace in our detectors. Experiments like Fermilab's Mini BUNI have spotted anomalies hinting at their existence, but the evidence is like catching a shadow at the edge of your vision. They're one moment, gone the next. What's at stake isn't just a census of cosmic neutrinos. If sterile neutrinos are real, they could be the invisible architects behind dark matter, or even portals to higher dimensions. Picture this: every second, a river of these undetectable particles might be flowing through you, carrying secrets about why galaxies spin too fast or how the universe avoided annihilating itself in the Big Bang. The solar neutrino problem taught us that nature loves a good disguise. Now, the hunt is on to see just how many more masks the cosmic neutrino background might be wearing. There's a cosmic coin flip at the heart of particle physics, and its outcome could reshape our understanding of reality. It's called the neutrino mass hierarchy problem, and it boils down to a deceptively simple question: which neutrino weighs the most? You'd think after proving these particles have mass, we'd have this sorted, but nature loves a good curveball. Right now, scientists are split between two possibilities: the normal hierarchy, where the neutrino flavors we know have a tidy, ladder-like mass order, and the inverted hierarchy, which flips that ladder upside down in a way that defies conventional physics. And here's where it gets cosmic. The answer might be frozen into the neutrino background itself, like a secret etched into the universe's oldest ice. Picture the normal hierarchy first. In this scenario, the three neutrino flavors electron, muon, and tau stack up like steps on a staircase, each slightly heavier than the last. It's the intuitive arrangement, mirroring how other fundamental particles organize themselves. But the inverted hierarchy, that's where physics starts feeling like a surrealist painting. Here, the lightest neutrino becomes the middleweight, sandwiched between two heavier siblings, creating a valley where you'd expect a peak. It's as if electrons suddenly decided to orbit atomic nuclei in hexagons instead of spheres, technically possible, but deeply unsettling to everything we thought we knew. Why does this matter? Because neutrino masses aren't just entries in a physics spreadsheet, they're cosmic sculptors. Their gravitational tug over 14 billion years could explain why galaxies cluster the way they do, or even why antimatter lost its battle against matter in the early universe. In the normal hierarchy, neutrinos would have subtly guided structure formation like a gentle current, but inverted, that might imply wilder, less predictable influences, like hidden interactions with dark matter or cracks in the standard model big enough to drive a quantum truck through. The cosmic neutrino background is our time machine here. Normal versus inverted hierarchies would leave different fingerprints in how these ancient neutrinos are distributed. One might show smoother variations across space, while the other could reveal sudden dips or spikes, clues written in particles that outlasted stars. Experiments like Juno in China and Dune in the U.S. are racing to catch these fingerprints by analyzing how neutrinos oscillate over long distances. But there's a catch: the differences are vanishingly small, like trying to spot a single misspelled word in a library of galaxies. And then there's the existential twist. If the hierarchy is inverted, it could mean neutrinos obey rules unlike any other particle's rules that might require new forces, extra dimensions, or even a cosmic bias toward matter over antimatter. Some theorists whisper that an inverted hierarchy could be a relic of the universe's very first phase transition, a quantum hiccup that tilted reality in favor of existence as we know it. That's the gamble hiding in this cosmic coin flip. Heads, and the universe makes orderly sense; tails, and we might need to rewrite physics from the ground up. The universe holds its secrets close, but few are as tantalizing as the possible handshake between neutrinos and dark matter. We know dark matter exists because galaxies spin faster than they should. Clusters bend light more than visible mass can explain, and cosmic structures grew too quickly after the Big Bang. Yet after decades of hunting, we still don't know what it's made of. Enter relic neutrinos from the cosmic neutrino background, particles so shy they make ordinary neutrinos seem outgoing, which might be hiding in plain sight as part of the invisible scaffolding of the cosmos. Here's the puzzle: dark matter outweighs normal matter 5-to-1, but neutrinos we've detected are far too lightweight to account for it. That's where sterile neutrinos come in, theoretical shadow particles that don't interact with any force except gravity. Unlike their known cousins, sterile neutrinos could be heavy enough to tug galaxies into shape without ever leaving a trace in our detectors. And if they exist, they'd likely be woven into the cosmic neutrino background, frozen relics from the universe's first moments. Finding them would be like discovering a hidden ingredient in the recipe for reality. Some theories suggest sterile neutrinos could decay into bursts of X-rays, leaving faint fingerprints in galaxy clusters. Others propose they oscillate into regular neutrinos at rates so slow we've yet to catch them in the act. The kicker: if sterile neutrinos are out there, they'd solve multiple cosmic riddles at once. Their gravity could explain dark matter's grip on galaxies, while their quantum behavior might reveal why the universe didn't annihilate itself in a storm of matter-antimatter collisions after the Big Bang. Experiments are closing in. Telescopes like NASA Chandra hunt for unexplained X-ray emissions from distant galaxies' potential sterile neutrino decay signals. Underground labs refine detectors sensitive enough to spot oscillations vanishingly rarer than solar neutrinos' transformations. Even the cosmic neutrino background itself could betray sterile neutrinos through subtle ripples in spacetime, imprinted when the universe was less than a second old. But the real twist: if sterile neutrinos aren't the answer, the cosmic neutrino background might still hold clues. Some models suggest ordinary neutrinos, though too light to be dark matter, could have guided its distribution like cosmic shepherds, herding it into the filaments and voids we see today. Their gravity, faint as it is, might have nudged dark matter into the structures that later birthed galaxies. Either way, the hunt reshapes our tools. To catch sterile neutrinos, we're redesigning detectors to pick up signals 1,000,000 times fainter than current limits. We're even mining old supernova data, asking whether anomalies like the neutrino pulse from supernova 1987 might have been sterile neutrinos in disguise. The stakes couldn't be higher. If relic neutrinos and dark matter are connected, we're not just solving a mystery, we're rewriting the story of how the universe built itself. Every particle with an electric charge, like electrons or protons, acts like a tiny bar magnet, a property called the magnetic moment. But neutrinos, they're electrically neutral, so by all known laws, they shouldn't have won. Yet here's the twist: some experiments hint that neutrinos might defy this rule, sporting what physicists call a neutrino dipole moment. If true, it would mean these ghostly particles carry a hidden magnetic fingerprint, one so faint it's like detecting a compass needle on the moon from your backyard. And that minuscule signal, if it exists, could rewrite the standard model while unlocking bizarre behaviors in the cosmic neutrino background. Where would a neutrino's magnetic moment come from? The leading theory points to quantum loops, tiny, ephemeral distortions in spacetime where virtual particles pop in and out of existence. In most particles, these loops cancel out neatly, leaving no magnetic trace. But neutrinos, with their bafflingly small masses and tendency to oscillate between flavors, might allow these loops to leave behind a residual wobble like a spinning top that ever so slightly veers off course. The effect would be unimaginably small. Estimates suggest the neutrino's magnetic moment could be 1,000,000,000 times weaker than an electron's. Yet in the vast sea of the cosmic neutrino background, even this faint magnetism could have cosmic consequences. Imagine ancient neutrinos, particles that have traversed the universe since its infancy, interacting with primordial magnetic fields. A dipole moment would mean these neutrinos could align like compass needles in cosmic magnetic fields, subtly changing their trajectories over billions of years. That alignment might leave faint patterns in how relic neutrinos are distributed today, clumps or voids that shouldn't exist if neutrinos were truly indifferent to magnetism. Some theorists even speculate that these magnetized neutrinos could have influenced the universe's first magnetic fields, acting as invisible conductors in the early plasma. The hunt for this effect is pushing detectors to their limits. Experiments like GEMMA in Russia and XENO-NNT in Italy are searching for telltale energy shifts when neutrinos scatter off electrons, a sign they're responding to magnetic fields. Others are scouring the cosmic microwave background for anomalies that relic neutrinos' magnetism might have imprinted. But the real prize, catching neutrinos in the act of flipping their magnetic orientation, a quantum dance that would confirm the dipole moment exists. Why does this esoteric property matter? Because the standard model predicts a neutrino magnetic moment so small it's practically zero. If experiments find anything larger, it's a flashing neon sign pointing to new physics, perhaps extra dimensions, undiscovered particles, or forces that only neutrinos feel. It's like finding a single misplaced stitch in a tapestry and realizing the whole design is woven differently than you thought. And buried in the cosmic neutrino background, that stitch might be waiting, a humble clue to the universe's deepest blueprints. The universe is expanding, but how fast? That seemingly simple question has divided cosmologists into rival camps, each armed with precise yet conflicting measurements. This is the Hubble tension. State-of-the-art telescopes peering at distant supernovae say space is stretching apart about 10% faster than the cosmic microwave background predicts it should. The discrepancy isn't just academic, it could signal a crack in our understanding of physics itself. And now, scientists are asking whether ghostly neutrinos from the cosmic neutrino background might hold the key to closing this gap. At the heart of the tension is a cosmic yardstick problem. To measure expansion, astronomers use two main methods. The first tracks the brightness of exploding stars and galaxies, building a distance ladder rung by rung into the cosmos. The second analyzes the CMB's faint ripples, frozen echoes of the early universe's density variations. Both methods are meticulous, both have been refined for decades, and yet they stubbornly refuse to agree. Enter neutrinos. These particles may be nearly massless, but their gravitational influence over billions of years could subtly warp how we interpret both sets of measurements. Here's how it might work. Neutrinos from the CNUB have been streaming through space since the universe's first second, their combined gravity gently tugging at matter like an invisible tide. If they have even slightly more mass than we've assumed, that extra pull could have altered how galaxies clustered over time, skewing our distance ladder calculations. Alternatively, their presence might modify how sound waves propagated in the early plasma, tweaking the CMB's ruler in ways we haven't fully accounted for. It's like realizing the tape measure you've been using all along was stretching imperceptibly, throwing off every blueprint, but the plot thickens. Some theories suggest neutrinos didn't just passively nudge cosmic structures, they might have morphed. If sterile neutrinos exist, their sudden appearance or decay could have injected extra energy into the young universe, temporarily juicing its expansion rate. Others propose that neutrino interactions with dark energy, the mysterious force accelerating the cosmos, could explain why local and ancient measurements diverge. Imagine dark energy as a river's current. Neutrinos might be invisible rocks beneath the surface, splitting the flow into conflicting streams. The stakes are high. If neutrinos resolve the Hubble tension, it could validate their role as cosmic sculptors while preserving our current models of cosmology. But if they don't, physicists might need to entertain wilder ideas, like an undiscovered particle, a flaw in Einstein's gravity, or even ripples from a collision with another universe. Experiments like DAISY and the upcoming Rubin Observatory are racing to map millions of galaxies, hunting for neutrino fingerprints in the large-scale structure of space. Meanwhile, theorists are running supercomputer simulations where they dial neutrino masses up or down, watching how the virtual cosmos responds. One thing's certain, the Hubble tension isn't just about numbers. It's a tug-of-war between the universe's youngest light and its oldest particles, and the cosmic neutrino background is the dark horse that could tip the scales. Whether neutrinos ultimately heal the rift or deepen the mystery, their whisper from the dawn of time is reminding us that some of cosmology's biggest answers might be hiding in the smallest details. At the very edge of what we can see, where the observable universe fades into the unknown, there might be an invisible barrier built from the universe's oldest ghosts, neutrinos piling up like cosmic driftwood after a 14 billion-year tide. This is the theoretical neutrino wall, a frontier where relic neutrinos emitted shortly after the Big Bang could be stacking up, trapped by the expansion of space itself. Picture it, particles that have traveled uninterrupted since the dawn of time, finally meeting a point where the stretching fabric of the cosmos outruns them, leaving them stranded in a vast, thin shell at the limits of our vision. The idea hinges on a startling property of neutrinos and expansion. Early in the universe's history, space stretched so rapidly that some regions moved away from us faster than light could cross the gap. Neutrinos, though speedy, couldn't outpace this expansion forever. Eventually, the ones emitted from the most distant reaches would find themselves frozen, in place relative to us, their light-like speed no match for the runaway stretching of space. The result, a spherical boundary roughly 16 billion light-years away, where these ancient neutrinos accumulate, too distant and diffuse to detect directly, yet potentially warping the universe in ways we're only beginning to model. What's wild is how this wall could reshape cosmology. If it exists, its gravitational influence might subtly bend light from objects behind it, creating distortions in the cosmic microwave background or warping the apparent positions of faraway galaxies. Some theorists speculated could even explain anomalies in the Hubble constant, those nagging discrepancies in the universe's expansion rate, by adding an extra layer of gravitational drag at the edge of the observable cosmos. Others wonder if the neutrino wall might act like a funhouse mirror for high-energy particles, reflecting cosmic rays in unexpected directions or filtering certain energies as they pass through. But here's the catch: proving its existence is like trying to photograph a shadow cast by smoke. The wall's neutrinos would be unimaginably sparse, perhaps just a few per cubic meter, and their energy would be drained to near nothing by the universe's expansion. Current detectors built to catch neutrinos from supernova or the sun are utterly deaf to these whispers. Yet hope isn't lost. Future observatories like NASA proposed Ptolemy experiment aim to catch relic neutrinos by their minuscule interactions with ultra-cold materials. Others are scouring the CMB for telltale imprints, like faint concentric ripples that could betray the wall's gravitational fingerprint, the most tantalizing possibility. That the neutrino wall isn't just a fossil, it's a fence. Beyond it could lie regions of the universe forever hidden from us, their light and neutrinos too far away to ever reach us, no matter how long we wait. If true, this barrier would mark not just the edge of what we see, but the edge of what we can see, a cosmic horizon built not by distance, but by the very laws of physics. And that raises a haunting question. Are we, like goldfish in a bowl, forever limited to observing only the universe's reflection on the walls of our own tiny corner? Among the greatest unsolved puzzles in physics is how gravity, the force that sculpts galaxies and bends light, fits into the quantum world. At subatomic scales, gravity seems to vanish into the background, utterly drowned out by other forces. Yet somewhere, in realms we can't yet probe, it must merge with quantum mechanics. And shockingly, the cosmic neutrino background might be hiding the first experimental clues to this unification. These ancient particles, forged when the universe was a seething quantum soup, could carry imprints of spacetime's granularity, a ledger of gravity's behavior at the smallest scales. Think of spacetime as a vast ocean. On the surface, it's smooth, predictable, but zoom in close enough and you'd see chaotic froth, quantum fluctuations where space and time churn like boiling water. These trembles are too tiny to spot with today's instruments, but neutrinos traveling uninterrupted for billions of years might have recorded them. Every oscillation, every flavor shift they experienced could bear scars from brushing against spacetime's quantum foam. The patterns in the CNUB might be a Rosetta Stone for decoding gravity's quantum language. How theories like loop quantum gravity suggest space isn't continuous but built from indivisible atoms of spacetime, tiny loops or grains. If true, neutrinos traversing the early universe would have jittered slightly as they crossed these microscopic bumps, altering their propagation in ways that could now appear as anomalies in their relic distribution. String theory offers another angle. Vibrating strings might generate extra dimensions, and neutrinos slipping through these hidden folds could emerge with telltale energy shifts. The search for these signs is pushing detector technology to the brink. Projects like Ptolemy aim to catch relic neutrinos with such precision that their energy spectra could reveal distortions, like finding a perfectly straight ruler with microscopic warps betraying the fabric it was cut from. Others analyze neutrino oscillations from distant supernova, hunting for delays or accelerations that wouldn't fit standard models. Even a minuscule discrepancy could signal quantum gravity at work. But the boldest idea, that neutrinos themselves are stitches weaving gravity into the quantum tapestry. Some models propose they're entangled with hypothetical gravitons, the theoretical carriers of gravity, acting as intermediaries between the quantum realm and cosmic scales. If the CNUB holds this connection, decoding it wouldn't just solve a mystery, it would reveal how space-time itself is spun from the universe's deepest laws. And that's a secret worth chasing, one ghostly particle at a time. If neutrinos can vanish, the universe might be playing the ultimate magic trick on us. The idea seems absurd at first. These particles barely interact with matter, so how could they possibly decay? Yet hidden in the cosmic neutrino background could be evidence that even ghostly particles aren't eternal. This is the neutrino decay paradox, the startling possibility that some of these ancient travelers have been disappearing en route across the cosmos, leaving gaps in the relic sea we expect to find. If true, it would mean the CNUB isn't the pristine time capsule we thought, and the implications would send shockwaves through cosmology. Picture the universe's first second again, when neutrinos flooded out in unfathomable numbers. Standard physics says they should still be here, their total count barely diminished after billions of years. But what if some decayed into even lighter particles or into nothing at all? Theories suggest this could happen through processes we've never observed, like neutrinos splitting into hypothetical majorons or leaking into extra dimensions. The effect would be subtle. For every million relic neutrinos, maybe a handful would have vanished. But over 14 billion years, those tiny losses add up, thinning the cosmic neutrino background like a fading echo. The hunt for this missing signal is turning astrophysics into detective work. One clue could come from supernova. When a star explodes, it blasts out neutrinos in a seconds-long burst, a pulse that detectors like Super Kamiokande can catch. If neutrinos decay, the ones from distant supernova should arrive slightly depleted compared to closer bursts, like a flashlight dimming with distance. So far, data from supernova 1987 shows no clear deficit, but the statistics are slim. Future explosions in our galactic neighborhood could tip the scales. Another approach probes the CNUB's gravitational footprint. If relic neutrinos have decayed, their collective gravity would weigh less on the large-scale structure of the universe, subtly altering how galaxy clusters form. Telescopes like Euclid are mapping cosmic structure with nanometer precision, searching for voids or distortions that decay might leave behind. There's even a wild card. If neutrinos decayed into radiation, that energy could have reheated the early universe, leaving fingerprints in the cosmic microwave background's polarization patterns. But here's where it gets thorny. Neutrino decay isn't just about missing particles, it's a potential window into physics beyond the standard model. Ordinary particle decays involve emitting something: photons, electrons, even other neutrinos. But if neutrinos vanish without a trace, it might mean they're tapping into hidden sectors of reality, like dark energy fields or extra dimensions. Some models even tie decay to neutrino mass, suggesting lighter flavors disappear faster, a cosmic survival of the heaviest etched into the CNUB. The stakes are dizzying. If decay is real, it could explain why the cosmic neutrino background seems fainter than predicted. or why dark matter surveys find less clumping at small scales. It might also mean the universe's oldest particles are actively erasing their own history, leaving us with only fragments of the Big Bang's original signal. Until detectors grow sensitive enough to catch a relic neutrino in the act of vanishing, this paradox remains one of cosmology's most tantalizing what-ifs, a reminder that even the universe's quietest whispers might still be hiding secrets. One of the greatest enigmas in physics isn't just why the universe exists, but why it's made of anything at all. According to the Big Bang, matter and antimatter should have been created in equal amounts, annihilating each other in a blinding flash that left behind nothing. Yet here we are, somehow about 1 in every billion matter particles survived, building everything from stars to smartphones, the culprit behind this cosmic cheat code. Neutrinos specifically, their role in a process called leptogenesis, where the tiniest particles in existence might have tilted the scales toward a matter-dominated universe. At the heart of this mystery is the seesaw mechanism, an elegant but unproven theory that links neutrino mass to the universe's matter surplus. Here's how it works if neutrinos are their own antiparticles, a property predicted by physicist Eta Majorana. Then heavy, unseen neutrino variants could have decayed asymmetrically in the early universe, producing slightly more matter than antimatter. Imagine a cosmic teeter-totter, on one side extremely heavy, sterile neutrinos, on the other the lightweight flavors we detect today. As the heavy neutrinos decayed, they'd tilt the balance toward matter, leaving behind the ghostly cosmic neutrino background as a receipt for this transaction. The CNUB is more than a relic here, it's a forensic snapshot. Leptogenesis would have occurred when the universe was just a trillionth of a second old, seeding it with excess electrons and neutrinos. Over time, these electrons fed into processes that built protons and neutrons, collectively called baryons, while the neutrinos drifted away, preserving a record of that initial imbalance. Today, the CNUB's temperature, density, and flavor ratios could hold encrypted clues about how much matter leptogenesis actually produced. But proving this isn't just about spotting neutrinos, it's about catching them in an identity crisis. If neutrinos are Majorana particles, they should occasionally exhibit a vanishing act called neutrinoless double beta decay, where two neutrinos annihilate each other inside atomic nuclei. Experiments like Germany's JERDA and the planned Legend project are hunting for this ultra-rare event in underground vats of germanium and xenon. Success would confirm that neutrinos are their own antiparticles, validating the seesaw's foundation. The stakes: if leptogenesis is real, the cosmic neutrino background isn't just a bystander, it's the smoking gun for why galaxies, planets, and you exist. Its delicate asymmetries might encode how a universe born perfectly balanced chose matter over oblivion, and that turns these ghostly particles from cosmic afterthoughts into architects of reality itself. The cosmic neutrino background appears almost perfectly uniform, a vast, smooth sea of particles stretching across the cosmos. But look closely enough, and faint ripples might emerge, tiny variations in density that could rewrite our understanding of the universe's infancy. These anisotropies, as small as 1 part in 100,000, are like cosmic braille, encoding secrets about how the first structures in existence began to clump together. Unlike the cosmic microwave background, which freezes the universe at 380,000 years old, the CNUB's fluctuations would date back to just 1 second after the Big Bang, a time when gravity itself was still finding its footing. Back then, space was so dense that matter and energy were locked in a violent tug of war, with neutrinos slipping through the chaos almost unaffected. But almost is the key word. Quantum fluctuations from the universe's birth would have imprinted subtle overdensities in the neutrino sea, regions where these particles clustered ever so slightly. Over billions of years, those infinitesimal wrinkles could have acted as gravitational seeds, steering ordinary matter into the galaxies and voids we see today. Detecting these fluctuations is like trying to hear a single note in a symphony played at the edge of the universe. The CNUB's neutrinos have lost almost all their energy to cosmic expansion, cooling to just 1.95 degrees above absolute zero. Their signals are drowned out by trillions of louder, younger neutrinos from the Sun, supernova, and even nuclear reactors on Earth. To spot anisotropies, we'd need instruments sensitive enough to distinguish relic neutrinos from this cacophony, while also mapping their arrival directions with precision finer than a billionth of a degree. Yet the payoff would be astronomical. If we could read these patterns, they'd reveal the universe's primordial gravitational landscape, showing where dark matter first pooled and how the cosmic web began knitting itself together. Some models suggest the CNUB's anisotropies might even expose cracks in inflation theory, hinting that the universe's explosive expansion wasn't perfectly smooth after all. Others speculate they could contain echoes of phenomena we've never seen, like cosmic strings or phase transitions from when fundamental forces split apart. The hunt is already pushing technology to its limits. Proposed experiments aim to exploit neutrinos' weak interactions in mind-bending ways, like tracking minuscule heat signatures in ultra-cold crystals or watching for atomic spin flips in diamond lattices. Another idea involves catching the CNUB's gravitational shadow, using the way its mass subtly bends light from distant quasars. It's a race against noise, against time, and against the universe's own reluctance to give up its oldest diary entries. But if we succeed, we might finally glimpse the blueprint of reality, written in particles that have been hiding in plain sight since the very first tick of the cosmic clock. Black holes don't just swallow light, they might be feasting on the universe's oldest neutrinos too. These cosmic vacuums warp space so severely that even particles as slippery as neutrinos can't always escape their grip. Imagine a river flowing toward a waterfall. The water near the edge gets dragged in no matter how fast it tries to move. That's what happens when relic neutrinos from the Cosmic Neutrino Background drift too close to a black hole's event horizon. Their journey, uninterrupted for billions of years, could end in an instant, vanishing into the abyss without a trace. But here's where it gets stranger. Black holes don't just consume neutrinos passively, they might reshape them. According to general relativity, the extreme gravity near a black hole stretches and distorts the paths of particles passing by, bending their trajectories like light through a funhouse mirror. For the CNUB, this means ancient neutrinos skirting a black hole could get lensed or amplified, their signals subtly twisted before reaching us. Some theories even suggest that supermassive black holes at galactic centers act like cosmic sieves, filtering neutrino flavors unevenly as they pass through, leaving behind a detectable imbalance in the relic sea. The real kicker, black holes might not just bend neutrinos, they could multiply them. Quantum field theory predicts that rotating black holes can amplify certain particle waves through a phenomenon called superradiance. If relic neutrinos interact with a spinning black hole's ergosphere, the region just outside its event horizon where space itself gets dragged into rotation, their quantum wave functions could be supercharged, emerging with heightened energy or even splitting into additional neutrinos. It's like whispering into a fan and hearing your voice echoed back louder. These neutrino echoes could carry distinct signatures, betraying the presence of otherwise invisible black holes lurking in interstellar space. Detecting these interactions would require instruments sensitive enough to spot the faintest distortions in the CNUB's uniformity. Gravitational lensing surveys, like those mapping dark matter, might one day reveal patches where relic neutrinos appear anomalously clustered or sparse, hinting at black holes warping their distribution. Meanwhile, next-generation neutrino observatories could hunt for unexpected hotspots in the cosmic neutrino fog, zones where the particle's energy or flavor ratios don't match predictions. Even the shadowy supermassive black hole at our galaxy's core, Sagittarius A, might leave fingerprints in the neutrino background if it's actively sculpting their flow. Yet the most tantalizing possibility lies in the unknown. If black holes alter relic neutrinos in ways we haven't predicted, their signatures could reveal entirely new physics, like extra dimensions crumpling near singularities or quantum gravity effects that only emerge in spacetime's most extreme environments. The CNUB isn't just a fossil, it's a messenger carrying encrypted notes from the universe's darkest corners, and black holes might hold the key to decoding them. The Cosmic Neutrino Background isn't just a relic, it's a time capsule sealed in the universe's first moments, carrying secrets about how every atom in existence came to be. To understand why, we need to rewind to when the cosmos was less than 20 minutes old, a frenzied epoch known as Big Bang nucleosynthesis. During this brief window, the universe was hot and dense enough to fuse protons and neutrons into the first atomic nuclei: hydrogen, helium, and trace amounts of lithium. But here's the catch: that process depended critically on neutrinos. These particles acted like invisible referees, dictating how quickly nuclei could form by controlling the balance between protons and neutrons in the primordial soup. Every second during nucleosynthesis, trillions of neutrinos buzz through the infant universe, colliding with neutrons and converting them into protons, or vice versa, through weak nuclear interactions. The rate of these conversions set the stage for how much helium versus hydrogen would survive. Too many neutrinos and the universe would have ended up starved of helium, too few, and stars today might lack the hydrogen fuel that powers them. The Cosmic Neutrino Background is the frozen record of that delicate dance, preserving the exact density and energy of neutrinos that shaped the first elements. Measuring the CNUB's properties today would be like uncovering the recipe for cosmic chemistry. For instance, the abundance of helium-4 in the universe is exquisitely sensitive to the number of neutrino flavors that existed during nucleosynthesis. If the CNUB reveals even a slight deviation from the 3 flavors we know, it could hint at undiscovered particles or forces active in the universe's first minutes. Similarly, the relic neutrino's energy spectrum could expose whether nucleosynthesis was interrupted by exotic events, like the decay of hypothetical heavy particles or sudden phase transitions in spacetime itself. Some theories go even further. If sterile neutrinos were present during nucleosynthesis, their extra interactions might explain why the observed lithium-7 abundance is 3 times lower than predicted, a discrepancy that's puzzled astrophysicists for decades. Alternatively, the CNUB might hold clues about whether the early universe experienced brief episodes of neutrino asymmetry, where matter and antimatter neutrinos briefly outnumbered each other, tilting the scales toward the matter-dominated cosmos we inhabit. The challenge, extracting these details, requires measuring the Cosmic Neutrino Background's properties with precision beyond today's technology. Experiments would need to detect not just the presence of relic neutrinos, but their exact energy distribution, flavor composition, and potential anisotropies, an undertaking akin to reconstructing a symphony from the faintest echo. Yet the payoff would rewrite textbooks. Confirming the CNUB's role in nucleosynthesis wouldn't just solve a cosmic mystery. It would give us the first direct evidence of how the universe's blueprint was drawn, element by element, in the fires of creation. And that's a time capsule worth cracking open. What if the reason neutrinos are so bafflingly lightweight is because they're partially slipping into realities we can't see? This is the spine-tingling premise behind theories that neutrinos might be cosmic interdimensional travelers, shuttling between our universe and hidden extra dimensions. While it sounds like science fiction, the math checks out, and the Cosmic Neutrino Background could be the perfect hunting ground for evidence. The idea stems from string theory, which proposes that the universe has more than the 3 spatial dimensions we experience. These extra dimensions could be curled up so tightly that only certain particles like neutrinos interact with them. Picture a hose stretched across a football field. From a distance, it looks one-dimensional, but up close, you realize it has a circular second dimension wrapped around its surface. If neutrinos are sensitive to such compact dimensions, even partially, their unusual properties start making sense. Their vanishingly small masses might be because some of their weight is leaking into these unseen directions, diluting their presence in our reality. How would this show up in the cosmic neutrino background? For starters, relic neutrinos might carry imprints of their extra-dimensional journeys. If they occasionally dipped into hidden realms during their 14-billion-year trek, their energy spectra could bear subtle anomalies, like hikers returning from a detour with mud on their boots. Some models predict these neutrinos would arrive with slightly less energy than expected, as if part of their momentum got lost in transit. Others suggest their oscillation patterns between flavors might betray interference from dimensions where physics operates differently. The most tantalizing clue could come from gravity. In some theories, extra dimensions modify how gravity behaves at tiny scales. If relic neutrinos interacted with these twisted gravitational rules early on, their distribution in the sinew B might show unexpected clustering or voids like shadows cast by invisible structures. Experiments like the upcoming Dune and Hyper-Kamiok are designed to catch these deviations, using ultra-sensitive detectors to measure neutrino energies and flavors with unprecedented precision. But here's the kicker: we might not need to detect the sinew B directly to spot extra dimensions. If neutrinos are leaking into hidden realms, today's high-energy collisions at particle accelerators like the LHC could produce them with missing energy, a signature that something carried it beyond our dimensional borders. Even cosmic rays striking the atmosphere might spawn neutrinos that vanish anomalously, their disappearance rates hinting at unseen dimensions. Of course, not all physicists are sold. Skeptics argue that extra dimensions are a convenient fix for problems that might have simpler solutions. Yet the beauty of this idea is its testability. Unlike some far-out theories, neutrino dimensional leakage makes concrete predictions. Specific energy deficits, flavor anomalies, or even new types of particle decays. Future sinew B measurements could either corner these phantoms or force us to ask whether the universe's shyest particles are hiding in plain sight, just beyond the edges of our perception. Before the first stars flickered to life, before galaxies spiraled into being, the universe was a roaring ocean of sound. Not sound as we know it, no air, no mediums to carry vibrations, but waves of compression and rarefaction racing through the primordial plasma, sculpting the cosmos in ways we're only beginning to decode. These were neutrino acoustic oscillations, and they left their fingerprints everywhere, in the distribution of galaxy clusters, in the faint hum of the cosmic microwave background, and most tantalizingly, in the ghostly sea of relic neutrinos still washing through space today. Think of the early universe as a colossal bell struck moments after the Big Bang. The clapper was the explosive release of energy, sending shockwaves rippling through the seething plasma of particles. Photons and electrons, tightly coupled in those first moments, pushed and pulled against each other like dancers in a cosmic tango. But neutrinos, they moved to a different rhythm. These particles, already slipping free of matter's grip, surfed the waves with unmatched speed, their gravity subtly amplifying certain oscillations while damping others. The result was a harmonic interplay, regions where neutrinos piled up like crests in a tide, and voids where they thinned to near nothingness. This neutrino symphony didn't just fade into silence. Those density ripples, frozen into the cosmic neutrino background as the universe expanded, became the scaffolding for everything that followed. Where relic neutrinos clustered ever so slightly, their extra gravitational pull attracted dark matter and gas, seeding the first overdense regions that would eventually collapse into galaxies. The scale of these imprints is staggering. Some neutrino sound waves stretched hundreds of thousands of light years across, leaving behind a cosmic fingerprint now visible in the vast walls and voids of the large-scale structure. Detecting these acoustic traces is like trying to reconstruct a symphony from a single, decayed note. The CNUB's oscillations are so faint that even the most sensitive experiments can't yet pick them out directly. But astronomers have found clever workarounds. By mapping the distribution of galaxy clusters with surveys like DAISY and Euclid, they're reverse engineering the neutrino sound wave's impact. Clusters should align at specific, predictable intervals, echoes of those primordial wavelengths. And the cosmic microwave background adds another clue. Its own temperature fluctuations bear slight distortions caused by neutrinos tugging at photons during their final scattering. Yet the holy grail remains catching the oscillations in the neutrino background itself. Future detectors might exploit a quirk of quantum mechanics. As relic neutrinos stream through Earth, their wave-like nature could interfere constructively or destructively depending on their original acoustic phase. Imagine tuning a radio to pick up static, except the static is a 14-billion-year-old echo of the universe's first vibrations. Success would give us more than a snapshot. It'd be a soundtrack of creation, revealing how gravity and particle physics waltzed together to build reality from chaos. What's astonishing is how much these silent waves could still teach us. Their wavelengths encode the universe's expansion rate during the first-second day that no other probe can access. They might even carry hints of unknown physics. If neutrinos interacted with dark matter or extra dimensions during those early moments, the oscillations could show subtle asymmetries, like a record warped by hidden forces. For now, the CNUB's music remains just beyond our hearing, but every new experiment brings us closer to turning up the volume on the cosmos' oldest song. The idea of parallel universes often feels like science fiction until you consider that the cosmic neutrino background might be carrying whispers from them. Among the wildest theories in cosmology is the notion that our universe is just one bubble in a vast multiverse, each with slightly tweaked physical laws. And if that's true, relic neutrinos could be the closest thing we have to a cosmic paper trail, their peculiar properties hinting at realities beyond our own. Think of it like this: during cosmological inflation, the rapid expansion that shaped our early universe, space-time may have bubbled into countless separate regions, each crystallizing with different fundamental constants. In some, gravity could be stronger; in others, electromagnetism might not exist. But here's where neutrinos get interesting. Their bizarrely small masses and tendency to oscillate between flavors are delicately tied to the Higgs field and quantum vacuum. If those fields vary even slightly in other universes, their neutrinos would too, perhaps with dramatically different masses, interaction strengths, or even extra flavors. The CNUB in our universe could be subtly imprinted with evidence of this multiversal tapestry. For instance, if inflation left behind defects like cosmic strings or domain walls, boundaries where physics shifts abruptly, relic neutrinos passing through them might bear scars in their energy signatures. Certain anomalies in their distribution, like unexplained clustering or gaps, could signal collisions with adjacent universes during the Big Bang's aftermath, like bruises from a long-forgotten cosmic fender bender. Even the neutrino mass hierarchy might be a clue. Why do we see 3 light neutrinos arranged in this specific order? In a multiverse, our configuration could be one possibility among infinite others, with most universes hosting heavier, sterile, or even non-existent neutrinos. The mere fact that our CNUB exists in its current form might reflect a rare, life-permitting balance, a cosmic lottery ticket where neutrinos ended up just right for galaxies and us to form. String theory adds another layer. If extra dimensions exist, neutrinos slipping between them could appear to us as intermittent, missing particles in the CNUB, their arrivals and disappearances betraying portals to other realms. Experiments hunting for sterile neutrinos or anomalous oscillation patterns might accidentally stumble on these interdimensional commuters, their data revealing not just new particles but entire universes. Of course, proving any of this is staggeringly hard. Multiverse theories often flirt with the untestable, but the CNUB offers a rare exception. Future detectors capable of mapping Relic neutrino anisotropies with nanometer precision might spot irregularities no single universe model can explain, patches where the neutrino sea inexplicably thins or ripples in ways that suggest external influence. Alternatively, statistical analyses of neutrino mass distributions could reveal unlikely fine-tuning, hinting at a wider landscape of possibilities. For now, it's a tantalizing what-if. But if the cosmic neutrino background ever coughs up evidence of a multiverse, it would mean these ghostly particles weren't just passing through walls or planets. They've been slipping between realities all along, stitching our universe into something far grander than we ever imagined. Detecting the cosmic neutrino background is like trying to catch fog with a butterfly net. The particles are everywhere, yet slip through every tool we've ever built. At this very moment, 1 billion Relic neutrinos pass through your thumbnail every second, but their interactions are so vanishingly rare that catching even a handful requires detectors of staggering sensitivity. The challenge isn't just technical, it's a cosmic game of hide and seek where the seekers are blindfolded and the hiders are ghosts. Take the proposed Ptolemy experiment, for example. Unlike traditional neutrino detectors that wait for particles to interact naturally, Ptolemy aims to actively capture Relic neutrinos using a radical approach: ultra-cold tritium-coated graphene. The idea is to exploit a quirk of quantum mechanics. When a neutrino collides with a tritium nucleus, there's a tiny chance it'll be absorbed, transforming the nucleus into helium-3 while emitting an electron. The electron's energy would betray the neutrino's presence, but here's the catch: Relic neutrinos have been stretched by cosmic expansion to energies millions of times lower than those from the Sun or supernova. Spotting their faint whispers demands cooling detectors to near absolute zero and shielding them from every stray vibration, cosmic ray, or trace of radioactivity. Even a single radioactive atom in the apparatus could drown out the signal. Then there's the neutrino capture method, which turns the problem inside out. Instead of waiting for Relic neutrinos to interact, some proposals suggest embedding targets like xenon or gallium deep underground, where the sheer volume of material increases the odds of a collision. But even with tons of ultra-pure material, the expected interaction rate is agonizingly low. Perhaps one event per year in a detector the size of a school bus. To make matters worse, these signals would be nearly identical to background noise from mundane sources like radioactive decay or cosmic rays. Filtering out the false positives is like trying to hear a pin drop in a hurricane. The real irony: the cosmic neutrino background is the closest neutrino source to Earth in terms of density, far denser than solar or supernova neutrinos, yet its particles are the hardest to detect because they've lost almost all their energy over billions of years. Modern detectors like Super Camiok, and brilliant at catching high-energy neutrinos from distant explosions, are practically deaf to the CNUB's feeble murmurs. That's why next-generation projects are rethinking the playbook entirely. Some aim to exploit quantum coherence, where Relic neutrinos might leave collective fingerprints in specialized crystals or superconductors. Others, like Anita, hunt for the CNUB indirectly by scouring Antarctic ice for radio waves emitted when ultra-high-energy neutrinos interact, though even that's a long shot. What makes this technological arms race so thrilling is the sheer audacity of the goal. Success wouldn't just mark a triumph of engineering, it'd be like inventing a telescope that sees not just light but time itself. A working Relic neutrino detector would peer further back than any instrument in history, offering a snapshot of the universe's first second. Until then, we're left chasing shadows, building machines at the edge of impossibility to hear whispers from the dawn of existence. And if history's any guide, the universe's quietest voices often tell the loudest stories. The universe isn't just a sea of galaxies, it's a labyrinth of voids, vast empty regions where matter seems to have vanished. These cosmic deserts, some spanning hundreds of millions of light years, aren't just empty by chance. They're sculpted by forces we're only beginning to understand, and the ghostly neutrinos of the cosmic neutrino background might be hiding in their shadows, quietly shaping the nothingness in ways that defy expectation. Here's the puzzle: galaxies aren't randomly scattered. They cluster into filaments and walls, weaving a cosmic web with voids between them. But when astronomers measure the motion of galaxies near these voids, they sometimes find peculiarities, small deviations from what gravity alone should dictate. One explanation: the gravitational tug of relic neutrinos, subtly warping the flow of matter even in the emptiest corners of space. Unlike photons, which are easily scattered or absorbed, neutrinos stream unimpeded through voids, carrying their faint gravitational influence like an invisible tide. The real surprise is how these voids could act as neutrino amplifiers. In dense regions, the signal from relic neutrinos is drowned out by the chatter of stars, gas, and dark matter. But in voids where the cosmic noise falls to a whisper, the subtle imprint of neutrinos might finally become detectable. Imagine shouting in a crowded room versus an empty cathedral. The latter lets every echo linger. Similarly, voids could magnify tiny anomalies in the sinew bee's distribution, revealing whether neutrinos cluster differently than predicted or interact with dark matter in ways we've never seen. Some theories go further, suggesting voids might be neutrino hotspots for entirely bizarre reasons. If sterile neutrinos exist, their decay could deposit energy in these regions, creating faint pressure waves that nudge galaxies at the void's edges. Alternatively, if neutrinos have even a tiny magnetic moment, their paths through voids could be warped by primordial magnetic fields, leaving a signature in the way galaxies drift around these empty spaces. The wildest idea: that voids aren't entirely empty. They could be strewn with neutrino dark streams, rivers of relic particles flowing along paths laid down in the universe's first second. The hunt for these clues is already underway. Surveys like the Dark Energy Spectroscopic Instrument are mapping millions of galaxies, searching for voids where galaxy motions betray unseen forces. Meanwhile, simulations crunch the numbers, testing whether adding neutrino effects like their slight gravitational pull or hypothetical interactions can explain observed void shapes better than standard models. The answers could rewrite cosmology. If voids prove to be neutrino laboratories, they might reveal why these particles are so lightweight, whether they're linked to dark energy, or even if the fabric of space itself has hidden textures we've yet to feel. In the end, the emptiest places in the universe might hold the richest secrets. By studying what isn't there, we could finally glimpse the ghosts that have been hiding in plain sight all along. Dark energy is the universe's greatest unsolved riddle, an invisible force stretching space apart faster and faster, defying gravity's pull. We know it makes up 68% of the cosmos, but we have no idea what it actually is. Enter the phantom connection, a radical idea that neutrinos, the universe's ghostliest particles, might somehow be entangled with this mysterious force. It's a hypothesis so daring it borders on heresy, but if true, it could mean these silent wanderers have been shaping cosmic destiny in ways we never imagined. The theory hinges on quantum vacuum energy, the seething foam of virtual particles that pop in and out of existence even in empty space. Normally, this energy is constant, but some models suggest neutrinos could alter it. Picture a ship sailing through the ocean. The water parts as it moves, then closes behind it. Now imagine that ship is a neutrino and the ocean is space-time itself. If relic neutrinos from the cosmic neutrino background interact with the vacuum in just the right way, their sheer abundance, billions per cubic meter, might subtly tweak the energy of empty space, adding fuel to dark energy's fire. One controversial version of this idea is called neutrino quintessence. Here, neutrinos don't just respond to dark energy, they become it. As the universe expands and these particles lose energy, their effective mass could morph into a repulsive force, accelerating cosmic expansion. It's like squeezing a sponge soaked in gasoline. The sponge dries out, but the released fuel ignites. In this case, the fuel is dark energy, and the sponge is the fading momentum of relic neutrinos. The risks of such theories are obvious. Tying neutrinos to dark energy requires rewriting quantum field theory and general relativity in ways that make even seasoned physicists uneasy. Worse, it risks creating a just-so explanation, one that's flexible enough to fit any observation without offering clear tests. But the reward, a unified framework where the universe's largest mystery and its smallest particles are two sides of the same coin. Experiments are already probing the edges of this idea by mapping how dark energy's strength changes over time using supernova, galaxy surveys, and the SIMBI scientists can check if its behavior aligns with neutrino-based models. Other teams are hunting for anomalies in neutrino oscillations or energy distributions that might hint at hidden vacuum interactions. Even the faintest deviation from expectations could be a clue that these phantoms are playing a larger role than we thought. The wildest twist comes from string theory, where higher-dimensional bulk neutrinos might leak gravity into our universe, mimicking dark energy's effects. It's a long shot, but if future detectors spot relic neutrinos with impossible energy signatures like particles that seem to arrive from nowhere, it could signal a crack in our dimensional walls. Whether this connection holds up or not, the mere possibility is electrifying. It forces us to ask, what if dark energy isn't some exotic field or undiscovered particle, but a side effect of particles we've known about for decades? The cosmic neutrino background might be more than a fossil. It could be the universe's quietest architect, sketching the future in strokes we're only beginning to trace. Time flows in one direction toward disorder, toward spilled coffee that never unstains your shirt, toward shattered glass that refuses to reassemble. This stubborn arrow of time, rooted in the relentless growth of entropy, has puzzled physicists for centuries. But buried in the cosmic neutrino background might lie a clue to why time marches forward at all, and how the universe's infancy set this irreversible course. Rewind to the Big Bang's first moments, when the universe was a near-perfect soup of particles, a state of astonishingly low entropy, like a deck of cards shuffled into perfect suit order. That improbable starting point is the reason time has a direction. Systems evolve from order to chaos, not the other way around. But here's the twist: something had to create that order in the first place. Recent theories suggest neutrinos, with their eerie indifference to almost all forces, could have acted as cosmic referees in those early moments, subtly biasing the universe toward a low entropy state. How neutrinos interact so weakly that they effectively decoupled from the rest of the cosmic plasma just 1 second after the Big Bang, freezing a snapshot of that pristine, low-entropy environment. While other particles kept colliding, heating up and muddling the entropy ledger, neutrinos sailed onward, preserving a record of that fleeting order. Today, their distribution in the CNUB might encode the original asymmetry that tipped the scales, why the past was orderly and the future chaotic. Some models even propose that relic neutrinos' gravitational tug subtly guided matter into clumps, accelerating entropy's rise by fostering galaxy formation. The real shocker: neutrinos might not just be witnesses to time's arrow. They could be its architects. Quantum mechanics suggests that certain particle interactions are time-symmetric, meaning they should look the same running forward or backward. Yet neutrinos break this symmetry in a process called CP violation, where matter and antimatter neutrinos behave differently. If this imbalance existed in the early universe, it could have planted the seed for time's one-way flow, like a hidden tilt in the cosmic playing field. Experiments like Dune and Hyper-Kamiok are now hunting for signs of this asymmetry in neutrino oscillations. A detection could mean these ghostly particles didn't just escape the Big Bang's chaos, they helped write time's rules on the way out. And if that's true, every second that passes is another tick of a clock wound up by neutrinos 14 billion years ago. Picture a neutrino born in the first heartbeat of the universe, a particle so ancient it witnessed the cosmos before starlight existed. Its story begins in a firestorm of pure energy, just 1 second after the Big Bang, when the universe was 1 trillion times denser than lead and hotter than a supernova's core. In that chaos, this neutrino wasn't alone. It was one of countless trillions forged in collisions so violent they make particle accelerators look like toys. But unlike photons trapped in the plasma's grip, this neutrino slipped free almost immediately, escaping into the expanding void like a dust mote fleeing a hurricane. For the next 380,000 years, while the universe remained opaque to light, our neutrino traveled unimpeded, a ghostly tourist passing through a cosmos still too hot for atoms to form. It sailed through the epoch of nucleosynthesis, when the first hydrogen and helium nuclei assembled, and felt the faint gravitational tugs of dark matter's invisible scaffolding beginning to clump. By the time the cosmic microwave background was emitted, the universe's first image, this neutrino had already been voyaging for longer than all of human history would last. As the cosmos expanded, stretching space itself, the neutrino's energy diluted from a blistering roar to a whisper. The once searing particle cooled to just 1.95 degrees above absolute zero, its wavelength stretched by the universe's growth like a rubber band pulled to the brink of snapping. Galaxies formed in its path, their gravity bending its trajectory infinitesimally, while black holes lurked like cosmic potholes, warping space-time around them. Yet through it all, the neutrino remained pristine, its quantum state unbroken, a time capsule sealed before the first star ignited. Today, this relic drifts through your body at nearly the speed of light, carrying encoded secrets in its flavor, energy, and trajectory. Its oscillations between electron, muon, and tau states might reveal how matter triumphed over antimatter. Its subtle gravitational deflection could map dark matter's distribution. And its sheer existence pins down the universe's expansion history with precision no telescope can match. But the most haunting part, this neutrino's journey isn't over. Long after stars burn out and galaxies fade, it will keep drifting. A silent witness to the universe's birth, its golden age, and whatever comes next. In its quantum spin lies a story older than atoms, older than light, waiting for us to learn its language. What if the universe isn't just strange? What if it's scripted? The cosmic neutrino background's eerie simplicity, a smooth sea of particles stretching back to the first second of time, has sparked a wild thought among some physicists. Could this pristine relic be a clue that reality is, well, rendered? It's not as far-fetched as it sounds. In a simulated universe, the CNUB's uniformity might reflect optimization, a cosmic background process running efficiently in the background, like a game engine reusing textures to save memory. No messy glitches, no unnecessary complexity, just clean, minimalist code disguised as physics. But before we dive down the rabbit hole, let's ground this in science. The simulation hypothesis, popularized by philosophers like Nick Bostrom, suggests advanced civilizations could create ancestor simulations so detailed their inhabitants wouldn't know the difference. If that's true, the CNUB's perfection might be a tell. After all, why would a simulation bother to simulate trillions of neutrino interactions per second when a statistical approximation would suffice? The relic background could be a placeholder, a mathematical shorthand for here be neutrinos, avoiding the computational overhead of tracking each one. Then again, Occam's razor slices through this neatly. The simplest explanation that the CNUB is smooth because the early universe was smooth requires no cosmic programmers. Physics as we know it predicts this uniformity naturally, neutrinos decoupled early, preserved their distribution, and voila, a fossilized sea of particles. No simulation needed, and yet the hypothesis lingers because it probes something deeper, our instinct to seek patterns, even in nature's austerity. The CNUB's elegance isn't just a feature, it's a Rorschach test for how we perceive reality. Scientists aren't building neutrino detectors to hunt for pixelated edges in the universe, but they are testing the simulation idea in other ways. If space-time has a finite resolution like a cosmic frame rate, high-energy particles like cosmic rays should reveal it. So far, they don't. Similarly, any rounding errors in fundamental constants would show up in precision experiments, yet the fine structure constant remains stubbornly consistent. The CNUB, meanwhile, behaves exactly as standard cosmology predicts, no shortcuts detected. Still, the simulation hypothesis thrives in the gaps, not the facts. It's a mirror for our awe, a way to marvel at the universe's crisp mathematical beauty without reducing it to mere machinery. Whether the CNUB is a relic of nature or someone else's design, its mysteries remind us reality, simulated or not, is far stranger than we imagine. And that's the real wonder, not the answer but the question itself. Imagine a detector so vast it spans continents, yet so precise it can sense the faintest tremor of a single relic neutrino passing by. This is the ultimate dream, an experiment that doesn't just glimpse the cosmic neutrino background but converses with it. Future physics might achieve this not with brute force, but by weaving quantum wizardry, artificial intelligence, and cosmic scale engineering into a machine that listens to the universe's oldest whispers. Picture a grid of quantum sensors buried deep in Antarctic ice, each atom chilled to near absolute zero. These aren't ordinary detectors, they're devices exploiting quantum entanglement, where a relic neutrino's infinitesimal nudge could disturb a perfectly synchronized dance of particles. The slightest interaction would ripple through this quantum network like a plucked string, amplified by AI algorithms trained to sift patterns from noise. Meanwhile, orbiting satellites crisscross the globe, tracing neutrino shadows cast by the moon's gravity, turning entire celestial bodies into lenses to magnify the CNUB's faint signal. The payoff, a 3D map of the neutrino background's anisotropies, regions where these particles clumped or thinned in the universe's infancy. These fluctuations could expose cracks in inflation theory, reveal dark matter's first interactions, or even hint at universes beyond our own. But the real revolution might come from time. If we could track relic neutrinos' paths backward, their trajectories undistorted by magnetic fields or matter, would point like arrows to their origins, effectively letting us see the Big Bang's first second in sharper detail than the cosmic microwave background ever could. We'd witness physics operating at energies a trillion times beyond what particle colliders reach, uncovering rules that governed reality before atoms, before light, before time itself settled into the rhythm we know. The ultimate experiment wouldn't just solve mysteries, it would teach us how to ask better questions. And that's the beauty of chasing ghosts. Sometimes they lead you to truth you never thought to imagine. From the universe's first whispers to the voids between galaxies, the cosmic neutrino background ties together 25 mysteries that stretch our understanding of reality. These ghostly particles aren't just relics, they're active threads in a cosmic tapestry, weaving through questions about dark matter, extra dimensions, and even the arrow of time itself. Each mystery unraveled exposes new questions, proving that the universe guards its secrets fiercely, but leaves just enough clues to keep us searching. Think of the CNUB as a grand puzzle where every piece connects to something profound. Why do neutrinos have mass when they shouldn't? Could sterile neutrinos be hiding in plain sight? Did these particles nudge the universe toward matter instead of annihilation? The answers aren't just academic, they're keys to unlocking everything from quantum gravity to the fate of the cosmos. And the wildest part, we've barely begun scratching the surface. This isn't just a story about neutrinos. It's a reminder that curiosity is our most powerful tool. Every detector buried in ice, every satellite mapping the void, every theorist scribbling equations, they're all part of a collective effort to decode the universe's hidden language. And you're part of it too, so tell us, which of these 25 mysteries grips your imagination? Is it the neutrino wall at the edge of space-time? The eerie link to dark energy? Drop your thoughts below, and if you're hungry for more cosmic detective work, hit subscribe. The universe isn't done surprising us, and neither are we.